what kinds of problems can we solve with quantum computing that we might not be able to solve as efficiently with classical computing.
This was the game changer because prime factorization is believed to be a very hard problem for classical computers to solve. There was a useful problem, something that's used in a lot of things and important things like cryptography and so on, where quantum computers seem to provide an exponential speed up. And this is this is what we're looking for. There's a lot of things within quantum computing that makes information very delicate and intricate. And trying to use this to do machine learning tasks in a more efficient or better way is not that easy.
Amira, welcome to the Super Data Science Podcast. How are you doing today? Where in the world are you calling in from?
I'm good, thanks. I'm calling in from South Africa, actually. But yeah, thanks for inviting me. Thanks for having me. It's really nice to be here.
Nice. And yeah, we do get to enjoy your South African accent, which is wonderful. And our audience gets to enjoy my very sick, very deep voice. And we'll probably edit out my hacking coughs, but those are going to be happening in the recording at least. So yeah, the show must go on. So we have such amazing topics planned for you today, Amira. I think we're going to jump right into the technical questions because I want to squeeze in as much as we possibly can. I've been so excited. I've been excited for years to record an episode on quantum machine learning. And now that it's happening with an expert like you, yeah, I woke up this morning, even with my cold, it felt like Christmas morning or something, where I was like, oh my God, I'm going to learn so much today. So you recently joined the University of Amsterdam as a postdoctoral researcher where you're working on quantum computing. And you specialized in quantum machine learning in the past, and that might still be something you're doing at Amsterdam. So for our audience who might be new to both of these topics, quantum computing as well as quantum machine learning, can you provide a brief overview of these topics and why it's gaining so much attention?
Yeah, sure. So maybe we can start with quantum computing first. So I think most people have heard about this, but the short story is that we're trying to build computers. We already have small scale devices that work on different principles, right? They work on different rules, and these rules are what is described by quantum physics. And so the hope is to try and build these computers that work on quantum physics that we believe actually is a true description of nature. And hopefully with these new computers, we can start to do more interesting things by being able to model things more efficiently and at larger scales. So quantum computers are quite beautiful, like theoretically, and a lot of companies and universities are trying to build these things and scale them up. And now, of course, if we can imagine having quantum computers, which in principle should be able to do more interesting and hopefully more powerful things, the next step or the next question to ask is, can we use them for things like machine learning to make machine learning a little bit more interesting and more powerful? So this then, combining these two things, quantum computers with machine learning, introduced this field of quantum machine learning. And instinctively you might think, oh well, it's very obvious that we can make machine learning better if we put quantum computers, like more powerful devices, in there. But what we're realizing after a couple of years is that it's not so straightforward. There's a lot of things within quantum computing that makes information very delicate and intricate, and trying to use this to do machine learning tasks in a more efficient or better way is not that easy. So this is like the broad level concepts is trying to do machine learning better in some way, but while using quantum computers. So yeah, that's what I've been trying to do for the last couple of years, and what I'm still hoping to do a little bit of from the more theoretical side now at Amsterdam.
Nice. I mean, feel free to dig even more into, the kind of the technical aspects of this. Like, so for example, the key distinction, as far as I'm aware, as like an extreme novice with quantum computing, is that a key difference is that when we're working with classical computing, I guess we can call it in contrast, with classical computing, we have bits that are either zeros or ones. But with quantum computing, they're qubits, and they're not clearly zeros or ones. They're like a probability distribution or something more like that.
Yeah, that's a beautiful way to describe it and think about it. Exactly. So when we talk about qubits in a quantum computer, you can exactly think about you have some sort of quantum mechanical system. And these are just like a probability distribution over bits. And then ultimately, when you like want to observe the state of your system, this is famously known as like the quantum measurement collapse problem. When you look at the distribution of your bits, or you try to like understand or analyze it or measure it, then you immediately see a collapse to like one possible combination of bits, so like classical information again. But there's like a subtle difference here, because you might think, well, if it's a probability distribution over zeros and ones, how is this any different from making a classical computer probabilistic? So quantum computing is a little bit special in that the probability distribution is actually described better by what we call probability amplitudes, rather than like numbers between 0 and 1, real numbers. These probability amplitudes can take complex values, and so the distribution is a little bit different in that qubits can actually interfere with each other. So we can create what's called quantum interference. And so probability amplitudes can kind of like be amplified or cancel each other out. And so you can get like weird, strange quantum effects or quantum phenomena through this interference that you can't see with just making bits probabilistic in a classical sense. So these probability distributions are a little bit different. And as I alluded to earlier, the rules that govern quantum computers and these qubits, these quantum bits of information, is quantum mechanics. And quantum mechanics says that the evolution of your quantum system, or whatever physical system you have, the evolution is linear. So the dynamics that describe the evolution within these computers is linear. And if it's not, then you also get like weird, crazy things that can happen. Like I think you violate some fundamental physical properties, like maybe time travel becomes real and all these other strange things. So so the dynamics have to be linear. And yes, and I think importantly, what's easy to remember, or like what's important to remember for quantum computers, is that you start off with like some initial state, which can be described, as you mentioned, as a probability distribution over zeros and ones over bits. And you evolve this state with linear dynamics, right? So you can apply some linear operations. And as a computer scientist, like what might make this easy to think of is that quantum computing is described by a lot of linear algebra. So your initial state can be thought of as a very, very large vector. And the linear dynamics is just applying a matrix multiplication to this vector and evolving it. And these matrices and vectors have certain constraints attached to them. And then eventually, when you want to measure your system, then you kind of observe a particular bit string, and you can repeat your experiment over and over again to get an understanding of the true probability distribution that describes your quantum output, or like the bit string that you're expected to measure. So this is quantum computing. And then, of course, machine learning fits very naturally on top of this, because machine learning is also a lot of linear algebra. So what we're trying to do in the sense of quantum machine learning is try to understand a couple of things, like how can we encode data into these quantum states and evolve these quantum states that encode data in interesting ways, so that we can measure outputs that look like labels for a machine learning task, or maybe a probability distribution that we're trying to generate for a machine learning setting. So these are the kinds of high level questions that one can answer.
Let me try to like paraphrase that back to you. So with quantum computing, we have qubits instead of bits, and these qubits have probability amplitudes that have all kinds of like delicateness, but also nuance to them, that mean that they can represent information for some kinds of problems more efficiently than we can with classical computing. Uh, and then you mentioned there specifically that there's like linear algebra operations in the way that we interpret what goes on in these qubits. And because of that linear algebra, which, if we have listeners out there who have been kind of figuring out how to use machine learning algorithms themselves at home, as opposed to using like scikit-learn as some kind of like high level abstraction, if you try to implement it yourself, you quickly realize that there's lots of linear algebra operations that underlie that machine learning algorithm. And so similarly, you can take advantage of those linear algebra operations that we use in typical quantum computing and apply those to try to solve machine learning problems. Was that a
Yes,
reasonable
brilliant.
phrase?
Yes, and feel free to ask like more detailed questions, because I know I'm speaking at a very high level, but and it might sound all abstract. And if I use any jargon that, doesn't make sense, just let me know.
Yeah,
Like, yeah.
let's go into the time travel a bit more.
Oh no. Yeah, yeah, this gets very science fiction-y very fast, but yeah, the time travel aspect.
Well, but actually, some aspect of quantum computing that is very science fictiony, but as far as I can understand, is quite real, is quantum entanglement. Do you want to dig into that one a bit?
Yeah, sure. So I think entanglement sounds very spooky at first, and a lot of people think, wow, this is something crazy that two fundamental particles can become entangled, and then no matter how far you separate them in space, like one tells you information immediately about the other, like instantaneously about the other. But mathematically, this is like actually quite simple what entanglement means, right? It's like it's really very straightforward. And in fact, I encourage you to even Google like how to describe or how to even entangle two qubits. I mean, this is like really something quite trivial. So to me, this is, I like to think in terms of math. So like, nothing is really spooky or weird here. It's just that you cannot describe basically the state of one qubit without knowing the state of the other when they're entangled. So people get like, people get the impression that, wow, this is so strange because you can separate these things very far in space and kind of, it's almost like you immediately have information about something you shouldn't, right? Because if something is really, really far away, then I think Einstein kind of said that information shouldn't be able to travel faster than the speed of light. And so initially entanglement was thought to violate this, but actually not so, right? Because even though you kind of know the state of another qubit that's super far away, in order to communicate any information, you still have to like send it somehow, through a classical channel or something like that across space. So there is no violation, and to me there isn't anything spooky. But entanglement is indeed a resource for quantum computing. So it is shown that entanglement is useful in a couple of settings for things like communication complexity and other fields outside of machine learning. So indeed, it is something. It is a resource. It is a correlation that can exist between particles or qubits, if you want to call them that cannot be observed outside of like quantum mechanical experiments. So this is indeed, and of course, it also largely was the reason that the physics Nobel Prize went to the Bell experiments and stuff like this, I think last year. So yeah,
Mhm.
it's pretty cool.
What if you, as a data scientist, could not only inform decision making, but also drive it? As a leader within your organization, imagine confidently harnessing provably optimal decisions. Gurobi Optimization, the leader in decision intelligence technology, equips you to unlock the power of mathematical optimization and transform your organization. Trusted by 80% of the world's leading enterprises, Gurobi's cutting-edge optimization solver, lightweight APIs, and flexible deployment ease the transition from data to decision. Visit gurobi.com/SDS to get exclusive access to a competition showcasing optimization's importance with prizes for top performers. That's gurobi.com/SDS.
All right. So us talking about this, I was going to ask like how do the qubits get entangled? But actually, I realized that I have to ask an even more fundamental question before I can do that, which is, what is a qubit anyway? Like, what what's getting entangled when the qubits are entangled?
Yeah, this is a good question. And I should probably also start by declaring that I'm not a an experimental physicist. So, so
Yeah, yeah, yeah.
experimentalists are really the ones in the lab building these qubits and building these quantum computers. So I just sit, kind of with my pen and paper. But I think how we can think about it is quite simple, right? So in nature, we have a couple of fundamental particles that make up other particles and other things. But these fundamental particles, when we try to describe them, when we zoom into these tiny scales on these very small particles, this is when we realize that the classical physics we learn in high school starts to break down, right? This is when we realize that the true description is quantum. And so now what physicists are trying to do and people in the labs are trying to say, okay, um, how do we force these fundamental particles to actually exhibit quantum properties? And the answer is it depends. It depends which particle we have, and then it depends on like what we need to do to exhibit this quantumness. So, for example, there are companies and institutions trying to build quantum computers out of photons. So these are photonic-based quantum systems. So a photon you can think of as just like a pocket of light, right? So it's like a little. So you have a laser and you have photons that come out through this laser, and each photon can be thought of as a qubit. And so you can manipulate photons in certain ways, and these can act as your qubits. But you can also make qubits out of electrons, for example. So there are certain types of electrons that exhibit quantum properties when you cool them down to very, very low temperatures. So these are the beautiful chandelier quantum computers that you often see pictures of with, like, I think IBM and a couple of other companies trying to do these. So yes, so I think photons and electrons, these superconducting quantum computers or qubits, are probably the most popular ones you will see. But I think there are also other companies and people trying other things, like, for example, with ions, which are also a different particle. So they're trying to create, like, for example, IonQ, which is another company, trying to create qubits out of ions and using ion traps and so on. So yes, so I hope this, like, kind of gives a little bit of the intuition, is that, basically there are a lot of fundamental particles, and if we do different things to them, we can start to see quantumness. And to be honest, like, we have small scale devices with a couple of different attempts or different particles, but we don't know how to scale them up to large sizes that matter yet. So this is still an engineering problem that we have to figure out. And which one of these will win the race is something that I cannot say. And I think a lot of different people will have different opinions, but it will be a very exciting next couple of years to see what wins.
Right. So, yeah, it just kind of occurred to me, and maybe this is obvious to a lot of our listeners, and maybe I knew this before, but I just kind of repieced it together, is that qubit, QUBIT, that must stand for quantum bit.
Yeah,
That's
yeah, exactly.
probably, yeah, which is like probably where I should have started. But yeah, so these qubits can be made up of photons, electrons, or ions, potentially other materials. And yeah, as you're saying, the kinds of quantum computers that we have today, like how many qubits can we have in one quantum computer today?
Yeah, so I guess again, it also depends on the system.
Right.
Like IonQ in particular have over 100 for sure. IBM, Google, they have also in the hundreds. There are also some roadmaps for some of these companies where they project they will have like a couple thousand qubits in the next year or two. So this will be quite exciting. But to just give you an idea, so everything we have is kind of, I guess, in the order of hundreds, maybe if we're lucky, 1,000 in the next couple of years or so. But
Yeah.
just to give you a sense of, like, these qubits are still very noisy, meaning they still, like, they house a lot of error. So they're difficult to manipulate. They're difficult to kind of keep the quantumness in them. So they're very hard to use for practical purposes. So, like, I think only once we get to the order of millions will we be able to start to see, like, interesting, useful applications of quantum computers and in quantum machine learning as well.
Right. Yeah. So I guess we're kind of like, as a very loose parallel, we're kind of like where we were in like the 1950s or something with classical computing in terms of the number of bits that we can fit on a transistor and like the complexity of the computations we can do. Although my understanding, and you can tell me I'm completely wrong, but like my vague understanding is that because a qubit has so much more expressiveness than a classical bit, you can do more with fewer of them. So yeah, like it still makes sense to me that, okay, if we're going to be doing machine learning, we're going to need millions of qubits. That makes sense to me. But for like, it seems like the kinds of problems that we're seeing quantum computers solve, they're able to solve much more complex problems than a classical computer with that same number of bits would be able to do.
Hmm. Yeah, I'm so glad you brought this up, because maybe I didn't explain it too well initially. Because indeed, you're right. So I think, like, people love to make the statement that with just I forget the number, like 120 qubits or something, you can already, a quantum computer can already have more store more pieces of information than number of atoms in the observable universe, right? So so it sounds strange when I say to you that you need millions of qubits to do some interesting things. And that's because I left out an important piece, is that because these qubits are so noisy, we need to perform what's called error correction on top of that. So we really need to be able to kind of remove this error by having more qubits in there, creating more redundancy to be able to actually do accurate simulations or run accurate algorithms. So we need more qubits in there, not for storing information and doing things, computing interesting things, but rather for correcting these errors that we see. So we need quantum error correction to work, and this is why the number goes up into the millions to do interesting things.
Yeah, that is super interesting, and I had no idea about that. Isn't that also that kind of error correction? Is that related to, and maybe I'm completely misremembering this, but when we do quantum computing experiments, don't we often will run it several times to try to get a reliable average kind of the answer?
It is a little bit, but it's also it's a little bit different. So I should also say I'm speaking out of my breadth of expertise here by talking about error correction, because there are a lot of researchers just focusing on this area alone. So you're right, a quantum computer, like I said, you start with some initial state, like some quantum state, and you can think of this as a vector, and then you apply some linear operations that evolve your quantum state. And then what you can do at the end of your quantum experiment, you can observe your system, meaning you can get a classical bit string out of it. You can, see what it collapses to. But as you just said, this is just one of many possible bit strings we can observe. So to get an accurate description of the probability distribution over bit strings, you run your experiment multiple times and you get an average. But error correction is a little bit different in that when you actually physically evolve your system on a quantum computer, so when you apply individual gates to your qubits, meaning let's say you have a qubit in state 0 and you want to flip it to state 1, so you apply what's called an X gate, right, similar to classical computing. Because there's noise in these qubits, these gates that you apply are sometimes not doing what they're supposed to do. And so error correction means let's have some buffer qubits in there to make sure that the operations that we apply are actually the operations we want to see. So they kind of ensure quality of our actual operations in the quantum computer and not just about the output.
Very cool. All right. So I'm grasping here that with classical computing, classical bits, we probably since the very beginning, probably since transistors were invented, something about them is that they are very reliably either a 0 or a 1. We can be quite confident about what's going on with them. With quantum computing, as you've mentioned already in the show, just keeping them in that quantum state is quite fragile. And there's a lot of nuance in what we can interpret out of them, but simultaneously, because of this fragility, we need lots of repetition or redundancy or error correction to be able to collapse reliably into some kind of classical result.
Yeah, exactly. And I think it's also important to say that classically we need error correction as well. We've just managed to do it on classical computers in a much more efficient manner, right? So we still have to figure out how to scale this up in a better way on a quantum computer. I think we largely have a lot of good ideas. But because quantum information, like you just mentioned, is so fragile, it's not very easy. And also there exists a lot of fundamental problems. Like, for example, there is this no cloning theorem, meaning we can't just copy one state over to another qubit. You can't just copy the state of a qubit over to another. Whereas classically you can do this, right? So you can create redundancy and copies rather easily. And so this helps you with things like error correction. But on the quantum side, there are barriers to this. And so we have to do things a little bit more cleverly. And I think this is where all these ideas of quantum error correction come into play. So yeah, it's a super nice, nice area.
Yeah, super interesting. So really quickly before I start getting more into your area of expertise and really getting into quantum machine learning versus classical machine learning, that kind of stuff, just really quickly, at a high level, in terms of the hardware to make this work, um, like you've probably seen, like I've never seen a quantum computer, but you've probably seen them. Like, what are they like? Like, how big are they? Do they need like super cooling or something to work? Like, just at a high level, give us some color on what these quantum computers are like.
Yeah, sure. So I've been super lucky to see quite a few. So I think the first one I saw was IBM's, and the most distinct thing I remember about it was walking into the room, and the sound that these cooling devices makes is like really strange. I think if you Google it, you can Google like sound of a quantum computer, and it's like this strange machinery that sounds like every like couple of seconds. And this was like, and to be honest, I'm not an experimentalist. I don't really understand like what all these machines are doing. But I just remember also being so taken aback by the size, right? So this was a superconducting quantum computer that I saw, and it was this beautiful chandelier made of like real gold hanging from the ceiling, all these crazy tubes and things coming out of it. And I just thought, wow, like this is a really impressive, device. And indeed, these ones are the ones that need like really, really cold temperatures down at the bottom of the chandelier. So the room itself is not cold, but like yes, getting this part at the bottom super cold is the task. I was also really lucky to see a photonic based quantum computer by a company in Toronto named Xanadu, which I think they're now beyond startup status. So I won't call them a startup, but they're building or they have built photonic based systems, and there they have really cool offices. And I think their quantum computers are on the, if I'm not mistaken, it's on the top floor on the penthouse of a really tall building in Toronto. So I remember doing a tour there, and this was also really beautiful to see. But yeah, there they have like these tabletops where all these lasers now matter, right? And manipulating these photons is what's important. And I think the equipment just to get, for example, a table perfectly level is just crazy expensive. So there are a lot of
Right.
effort and time and things that go into all these computers. But yes, I think these are the only two types I've seen so far. I haven't seen an iron based quantum computer. I'd love to, but yeah, they're really beautiful.
Cool. Yeah, that was exactly the kind of color I'm looking for. Really rich descriptions. It's really funny that thing you mentioned about like getting a table perfectly level. There's an episode of Rick and Morty where Rick
Yes.
creates perfectly flat. He spends like all this time getting a perfectly flat surface, and it's obviously very silly. But then when people step on it, they're like, oh my goodness, it's so flat. Like it's just so perfect.
Yeah, doesn't
Um,
he have to like remove from Morty's memory the flatness because he steps on perfect level and he just freaks out too much? Yeah, I think he has to wipe it from his memory, right?
I think that's right. Yeah, 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 yeah. Yeah, so you watch that show as well?
Yes,
Regular viewer?
my cat is his name is Morty. So yeah.
That's funny. Yeah, I'm in desperate need of a new episode. It's been so long. I was just looking into this yesterday. At the time of recording, at least, it's been almost a year since there's been a new episode. So
Yeah, they do
Jonesing.
take their time. Yeah.
They do. But it's worth it. So yeah, all right. So beyond our Rick and Morty recommendation, what else do I have for you? So, um, yeah, so let's dig into a bit more of your expertise on quantum machine learning. So, what kinds of problems? I guess, and maybe it makes sense to kind of ease into this again with the quantum computing again, as opposed to specifically quantum machine learning. But what kinds of problems can we solve with quantum computing that we might not be able to solve as efficiently with classical computing? And then, yeah, the same question for like quantum machine learning. Like, why do
Mhm.
quantum machine learning? What's the advantage of that relative to some classical approach?
Yeah, this is a very good question. And to be honest, we don't have a lot of clear, concrete directions for broad problem classes that quantum computers can just, immediately provide blanket advantages to. So the most obvious one is the one that like caused all this excitement about quantum computing and got all the funding and things like this. And that's this problem of prime factorization, right? Which also goes into a lot of cryptographic schemes and so on. And I think this idea of Shor's factoring algorithm, which uses quantum computing to factorize very large numbers into their prime constituents. This was the game changer because prime factorization is believed to be a very hard problem for classical computers to solve, right? So I think the best known algorithms to approach this problem take exponential time on a classical computer. So what Shor did was introduce an algorithm on a quantum computer that takes polynomial time, right? So to solve this prime factorization problem. So this was super exciting because finally there was a useful problem, something that's used in a lot of things and important things like cryptography and so on, where quantum computers seem to provide an exponential speed up. And this is like, this is what we're looking for. But unfortunately, since then, there hasn't been many concrete things following up on this. Like, there hasn't been too many examples. So what researchers are trying to do now at a high level is look for these types of problems that quantum computers seem to be naturally suited for. And this is this whole field of computational complexity theory, studying the hardness of problems and how much resources is needed to tackle them, and where quantum computers can be beneficial. So to be quite frank, from this like complexity theory point of view, factoring is the best thing we have so far. And so we're still trying to find other types of problems that seem to be suited for quantum computers. And we don't have any like too much interesting things, I think, to say there yet. But I'm hopeful that we will soon.
Be where our data-centric future comes to life at ODSC West 2023 from October 30th to November 2nd. Join thousands of experts and professionals in person or virtually as they all converge and learn the latest in deep learning, large language models, natural language processing, generative AI, and other topics driving our dynamic field. Network with fellow AI pros, invest in yourself in their wide range of training, talks, and workshops, and unleash your potential at the leading machine learning conference. Open Data Science conferences are often the highlight of my year. I always have an incredible time. We've filmed many Super Data Science episodes there, and now you can use the code SUPER at checkout, and you'll get an additional 15% off your pass at odsc.com.
Super interesting. So then, so in terms of like practical applications, the cryptography thing you hear a lot, because you also hear it a lot in the context of like, all of our passwords are going to be meaningless and the internet's going to be a free-for-all, which like, I don't know if you have thoughts on that, but I feel like I've also, and this is like a vague memory, but somehow things like the traveling salesman problem, I feel like I've come across as like something that is like very hard for classical computers, famously. So like the traveling salesman problem, for any of our listeners that have done computer science, is something that'll be a really obvious problem. But with the traveling salesman problem, when you have, say, 3 cities that a hypothetical salesperson needs to travel between, it's very easy to figure out what's the optimal route between the 3 cities to like minimize travel time. But as you add in additional cities, a 4th city, a 5th city, a 6th city, it starts to, the compute complexity becomes like, I can't remember exactly if it's like polynomial or exponential, but it's like the complexity gets very, very hard, very fast. But somehow it's a super vague memory, but I feel like somehow quantum computers can do that like instantaneously, solve that kind of problem.
Yes, this is a good question to bring up. So I don't think so. So let me maybe cast this into
you know what I might have been thinking of?
Yeah.
I might have been thinking of genetic computing.
Okay, maybe,
Which like where there's like, I might be messing things up. This is like one of those classic things where you get
not at all. I think this is a really good thing to bring up, because even myself, I thought, quantum computers can encode information, like an exponential amount of information, into like a small number of qubits, right? So you would think that these very large combinatorial problems are something easy for a quantum computer to solve, and in particular, like this traveling salesman problem, because as you add in more cities, the number of combinations of cities you can visit starts to grow exponentially. So the problem becomes very difficult to find what's the best route. And we hoped that a quantum computer can kind of cast all these variables into a state of superposition, and maybe we can kind of understand in superposition, what's the best distance or something like that. But it turns out to not be so straightforward. And in fact, this traveling salesman problem is known to be an NP-hard problem under certain assumptions, right? So this means NP-hard means like basically basically requires a ton of resources to solve, regardless of the system you're looking at, whether it's quantum or classical. And maybe I should also say right now at the get-go that we don't believe, so NP-hard problems are kind of the hardest problems we can face in computer science, right? So these are like this traveling salesman problem, for example, and a few others. And we don't believe that quantum computers can solve NP-hard problems in an efficient manner. So we don't believe that they will give us like polynomial time algorithms to solve NP-hard, like really hard problems, right? So this is unfortunate, and a way to see this is also quite straightforward. There's one particular problem in computer science that's called the Boolean satisfiability. So SAT, S-A-T, the SAT problem. And SAT is known to be a very hard problem for a classical computer to solve. In fact, we don't know any sophisticated ways to solve this problem other than just brute force search, right? So this is like the best we can do classically, and this takes exponential time. And now with quantum computers, we know a very nice result called through Grover's search algorithm, right? So this is a search procedure that gives us a quadratic speed up over like classical search, unstructured search. So we know through the lower bounds of Grover that we can apply brute force search only at a quadratic speed up with a quantum computer. So in principle, if we can only solve SAT quadratically faster, we can't really hope to do anything interesting with the SAT problem. And SAT is at the foundation of all NP-hard problems in computer science. So most NP-hard problems kind of derive themselves from SAT. So it's like a really depressing kind of statement. It's like, oh, well, we have all these tons of hard problems, but quantum computers, can't really do anything interesting. But this is just a belief. It's not a proof, of course, but it doesn't mean that other problems aren't out there, right? That quantum computers can provide exponential speedups for, and they're still useful. So, for example, like factoring, which is not NP hard, or not believed to be NP hard, but it's still like kind of, we don't have any practical classical algorithms that can solve this efficiently. So yeah, I hope this sheds some light on this area.
Totally. That was everything you've said has been so fascinating and so interesting and novel to me. So yeah, thank you so much. Amazing. And okay, cool. So limited applications today where we know that quantum computing provides some big improvement over classical computing. One of those being or the one example being prime factorization. But then with quantum machine learning, why are people excited about that? Like, why were you excited about that? Why have you spent so much time researching it? Like, yeah, what is the potential in quantum machine learning? It sounds kind of like you're saying, well, we don't yet know of many other applications of quantum computing, and yet it seems like there could be something here with quantum machine learning. Like, why is it exciting? Why are people pursuing that?
Yeah, so maybe let's start by like rewinding a little bit as to what quantum machine learning is, or what do I mean when I speak about it? Because I think there are a lot of different ways to think about it, and then we can kind of motivate a little bit some of the successes, because you're right. I mean, from a complexity theory point of view, this very high level point of view, it seems a bit counterintuitive when I say like quantum computers aren't good for hard problems. But you'll see that I think there are still pockets and areas that quantum computers can be super useful for, and one of them is machine learning. So when I say quantum machine learning, there are a couple of ways to think about it. The first is like, well, in regular machine learning, we're always concerned with a data set, and we want to do something with that data. We maybe want to learn some structure, or we want to kind of apply some labels to a new piece of information that comes in from a distribution that looks like this data set, and so on. So there's usually some notion of data. And in the quantum machine learning picture, we can say, okay, maybe this data is something classical, like our pixels on a picture that we put into a vector. Maybe it's just a classical vector. But there's also this idea of or notion of quantum data, and what this means we can talk about a little bit later. But basically, when we have data in this quantum machine learning picture, we need to encode it into a quantum state. So we need to somehow get it into the quantum computer to be able to process it, right? So this is step one. Step two is then, once it's in the quantum computer, once it exists as a quantum state, what do we do to it, right? Like, how do we evolve the quantum state? How do we change it? How do we apply operations to it that's meaningful? And then the step three, the last step, of course, is how do we measure our quantum system to get an output that is useful for us in machine learning? Like, if we want to label the picture cat or dog, how do we interpret a bit string measurement, out of our quantum system such that it tells us it's a cat or a dog? And there are many different ways to do that. There are many different ways to encode data, to evolve it, and to read out. And so when people do quantum machine learning, 99% of the time, they're trying to study how these aspects work and how we should do them under certain assumptions, right? Because it's almost impossible to say, this is a blanket approach to encode every piece of information. This is a blanket approach to evolve every piece of information, and this is how you should read it out. It really always depends. It depends on the structure of your data, your specific machine learning task, and what it is you want to do, right? So quantum machine learning is really these three ingredients and understanding how these three things work: how to put the data into a quantum state, how to evolve it, and how to understand it in terms of a label for a machine learning task. So okay, so I hope that makes sense, and then we can
Makes
talk
perfect
about
sense.
some. Okay, good.
And yeah, I think I've got it. Yeah, with quantum machine learning, we need to first convert our data into a quantum state, and I do definitely want to dig later. I've made a note, and I'm not going to let it
Okay.
slide about this quantum data idea, which is completely novel to me. But yeah, so start with converting data into a quantum state, and then I wrote down perform operations, but you actually used a different verb or now. Like you what
Yeah, evolve,
in this
evolve, but performing operations,
evolve.
exactly the same thing, right? Yeah. So let's use
Okay.
that. Yeah, I think it's the same. You can think about
Evolve
the same way.
sounds cooler. We're performing operations in classical machine learning all the time. I want evolution. That sounds way cooler. Um, and then the third state, or the third step, sorry, is then converting back from the quantum state into something that we can easily interpret, like a vector of pixels or whatever.
Exactly. Yeah, that's exactly right. Okay, so then to your next point about now how would this be advantageous? And here there are a couple of interesting things or results that have come out, and I think probably the most intuitive one to a machine learning or data science audience is this idea of kernel methods and support vector machines, which quantum computers seem very naturally suited for. So for those of you, I just recap very quickly, the idea of a support vector machine and these kernel methods is, usually your data is given to you in a very messy sort of space or setting, right? So let's say you're given a ton of information, and now you want to kind of classify this information into two subsets, let's say cats and dogs, for example. So you can try to fit a very complicated classifier to say, okay, these are the cats and these are the dogs, and this is how I classify my data. But another thing you could do is you could take your data and you could map it to a different space such that it becomes really easy to separate your classes with a very simple classifier, like a linear classifier, right? So just drawing a line between these two data sets, these two subsets in your data. And how people typically do this is they take their data and they map it to a higher dimensional space. And there, in a higher dimensional space, things kind of become easy. You can have a hyperplane, which is you can think of it as a generalization of a linear classifier that separates your classes. So this is this idea of what a support vector machine does. It takes your data and it maps it by something called a feature map into a higher dimensional space, and then applies a linear classifier, right? So why is this interesting for quantum and quantum machine learning? Well, because the step one that I told you about, which is taking your data and encoding it into a quantum state, you can actually think of it as this map into a higher dimensional space. So you can think about taking your data and trying to encode it into a quantum state as a quantum feature map. And then you can apply these operations, which can be a linear classifier. So if you figure out a clever way to map your data onto a quantum computer such that you kind of already separating things in a nice way in quantum space, what we call it quantum Hilbert space, then this is super interesting and super useful, right? And moreover, if you show that this mapping is something very hard for a classical computer to do, then you're in the money, right? So there, like, you've got a useful kernel, or useful, I should say, feature map, and you can kind of use it for these machine learning tasks. So there have been some interesting results here where people have shown that certain quantum feature maps and quantum these quantum support vector machines and so on are classically intractable, meaning they're difficult for classical computers to do. But the one downside is that the data sets that seem to be amenable to these maps are very artificial. So they don't seem to be naturally suited for data that we have in nature and in real life. So people are still trying to figure out if there's a natural quantum feature map that suits data sets that we're interested in. So this is still an open question. So there's been some proofs that there are some hard things, that a classical computer can't do, but we still need to find some use cases for them.
Data science and machine learning jobs increasingly demand cloud skills, with over 30% of job postings listing cloud skills as a requirement today, and that percentage set to continue growing. Thankfully, Kirill and Atle, who have taught machine learning to millions of students, have now launched CloudWolf to efficiently provide you with the essential cloud computing skills. With CloudWolf, commit just 30 minutes a day for 30 days and you can obtain your official AWS certification badge. Secure your career's future. Join now at cloudwolf.com/SDS for a whopping 30% membership discount. Again, that's cloudwolf.com/SDS to start your cloud journey today.
Very cool. That was magnificently explained as well. Thank you so much. That was an absolute delight to hear. And the kind of, I guess, the summary point here is that with quantum support vector machines, with QSVMs, while there have been theoretical demonstrations that QSVMs provide, can in some circumstances provide a great speed up over a classical support vector machine solution, that is only the case with data that we aren't aware of, like data that are set up in a way that we don't seem to observe from some natural phenomenon that would typically occur and that we would be putting into our models.
Yeah, exactly. Yeah.
Well, that's super interesting. So the quantum support vector machines. So you in particular, this is kind of jumping into our next big topic area, but it's interesting that you went down the route of quantum support vector machines because you have written a groundbreaking paper called "The Power of Quantum Neural Networks." So, and you co-authored that with some amazing people, with a top quantum researcher, David Sutter, as well as a Fields medalist. So this is like a Fields medal is like the Nobel Prize for mathematics. And Alessio Figali has a Fields medal. And you co-authored this Power of Quantum Neural Networks paper with David Sutter and Alessio Figali. It's interesting to me because, and there's a funny parallel here where today, a conference like NeurIPS, Neural Information Processing Systems, it was created in the 80s to study artificial neural networks, which now we typically call deep learning. But through there was a period of time, kind of in the early part of this millennium, in the first decade of this millennium, where even at a conference like NeurIPS, which has neural in the name, everybody was doing support vector machines. And then it was like AlexNet, the AlexNet moment in 2012, where Jeff Hinton and his team at University of Toronto showed that deep learning is practical for image recognition at large scales. And that led to this reemergence of neural networks as the leading approach in machine learning and artificial intelligence for a broad range of problems. Not every problem for sure, but a lot of the AI advancements in the last decade have been made through deep learning, through neural networks. So it's interesting to me that you have this expertise in quantum neural networks, and yet it was still, support vector machines, quantum SVM, that you went to an example of first.
Yeah, I think yes. So you summarized the history of machine learning quite beautifully, and I think the reason people like kernel methods or these support vector machines, however you want to call them, so much is because they're beautiful to study from a theoretical point of view, right? So here, like they're easy to well, not easy, but they're at least a lot of known things that we can say about machine learning from the support vector machine picture. But neural networks, as you also mentioned, they just work so damn well, right? So like they just work for everything we throw at them. They just can do it. They can solve really, really complex problems in almost like a human-like fashion. So why? And researchers in machine learning have been trying to figure out from a theoretical point of view why, but it was mostly the empirical success that drove all the theoretical studies that came afterward, right? So, and to be honest, I think there's still so much we don't know from a theoretical point of view as to why these deep networks work so well. And then you might think, well, why do we ignore kernel methods if we can understand them theoretically? But the downside is we can't implement them so well. There's like a cost in training and optimizing these support vector machines that scales like something like quadratically in the number of I think in the data. So this is quite expensive, and I think neural networks this doesn't have this quadratic scaling. It's actually linear, right? So the cost there is far cheaper. So you can optimize much larger neural networks with billions of parameters than you can with these support vector machines. So the reason I mentioned support vector machine as an example now is because on the quantum side, it fits very naturally in a theoretical framework and understanding what you're doing. But whether this will be the thing that we use on a quantum computer or not is still open for debate. And my guess is probably not. And so then I guess this is a nice natural segue into, well, what are these quantum neural networks, right? Or what do these things look like? And are they quite similar to the classical neural networks that we know and love? And what a quantum neural network is, you can kind of understand it in one sentence, is it's basically a quantum circuit which consists of certain operations. You can think of them as matrix operations, but these operations are parameterized, so they depend on parameters. And just like normal machine learning, you need to figure out how to tweak and train and optimize these parameters to fit your data. So quantum neural networks are these parameterized circuits where now we have to like figure out how to optimize these parameters for our machine learning task. And so the reason we considered these class of models in this paper that you mentioned, this power of quantum neural networks paper, is because we wanted to see if they can do anything interesting. Do they offer us anything different over traditional classical neural networks? So this is what we tried to investigate here.
Yeah, super interesting. So it sounds like where we could be with quantum neural networks today is that unlike the quantum SVM example, we may not have yet identified. Well, actually, I mean, you tell me. I don't know why I'm. It like is there. So it sounds like with QSVMs, we have clear instances of situations, even if the data are not likely to be come across in the real world. We have examples of QSVMs being more efficient than classical SVMs. Is it the case that we're not quite there with quantum neural networks yet, or yeah,
exactly. Yeah, exactly. You're on the complete right way to think about it, right? Because how did we get there classically? Well, we have computers that we can, do interesting, fascinating things with. We can thanks to things like backpropagation, we can scale up neural networks to billions and trillions of parameters now, where we can train and optimize very large models at scale. But on the quantum side, we can't do this yet, right? So in fact, a lot of the research that I did while I was a student researcher at Google was really trying to see if we can get backpropagation scaling of resources on these quantum computers. And it's really tricky because of this problem that information is so delicate on a quantum computer, right? So we can't really say we have, this notion of what our next best quantum model is going to be, our sort of quantum neural network. which is, I'm using it a little bit differently now because, people use this term for parameterized models, but will it be the next, best neural network? Probably not, but we can't really run any impressive empirical studies yet because our quantum computers are still so small. So yeah, so it's unfortunate that we can't replicate the same sort of classical machine learning success with just try and see experiments. So we have to try and, like maybe analyze things a little bit more carefully from a theoretical point of view, because this is the only option we have right now.
Right. So the work that you've done, so things like your Power of Quantum Neural Networks paper, they are like theoretical machine learning more than
Yes, exactly.
empirically. Yeah. And
Mm.
so what you're saying with a paper like this is as we begin to scale up quantum computers orders of magnitude more from where we are today, from hundreds of qubits to maybe millions of qubits or something, at that kind of scale, then we will be able to do quantum neural net. We will be able to solve quantum neural networks. We'll be able to We'll be able to find optimal parameters with a quantum neural network, and these kinds of advantages will emerge then.
Well, I hope so, but we might still encounter some barriers, right? So for example, going to these large scales where we have billions of parameters is essential for quantum machine learning to be able to compete with large language models and things like this, right? So we have to be able to scale our quantum machine learning models up, but we're going to have to be able to train them, right, as efficiently as we can train neural networks. And this is where this idea of like backpropagation comes in. Can we replicate backpropagation, which, I'm sure most people listening here know that backpropagation is a recipe to compute gradients in a very efficient way of these super large neural networks. And this gradient information allows us to go back to our neural network and change our parameters so that we get a better function, like we get a fit to our data. But on a quantum computer, backpropagation is not so easy, because how do we kind of reuse information to like compute gradients efficiently? We can't really peek into our circuit at different points and like extract information, because as soon as we do, our information collapses, we lose it. So we're going to encounter some barriers when we scale up our quantum models, and we need to figure out a better way to optimize them and train them. And backpropagation scaling, or like resources that replicate backpropagation, is really hard to do. And so something we showed recently is that backpropagation scaling is pretty much impossible to achieve unless you have something called quantum memory available to you. And this is also something, maybe if you're interested, we can dive a little bit more into. But all I want to say is that, yeah, there are some like actual barriers there, that even if we have huge quantum computers, it's not so straightforward that we'll be able to like optimize them in the ways we can optimize neural networks.
Nice. Yeah. I mean, let's dig into some of these terms. So, yeah, quantum data, quantum memory. Feel free
Yeah,
to pick which one you think is the natural one
sure.
to define next.
Yes, sure. So I'm glad we get a chance to talk about this, because I think this is a rather, well, at least to me, this is like a new area. And this is super exciting because a lot of new results have come out recently, by some researchers at Caltech and Google, that show some really positive things in this direction. So, okay, so what is quantum data? Well, I mentioned that you can think of a quantum state as like a vector, that encodes some information for your machine learning task. So maybe it encodes like some information about, let's say your data set consists of properties of cats and dogs, right? Like their weight and their height and their color and so on and whatever. And you figure out a way to kind of encode this information into a vector, right? So you can pretty much like list, let's say, the numbers in a vector, somehow. And then your first step is to encode this into a quantum state. So, there are lots of different ways, but you can imagine that, let's say you apply some operations to your in your quantum computer that depend on the values of these vectors, right? So let's say you're like doing rotations about an angle that depends on like the weight of your cat or something like this. It seems very artificial, but this is actually something people do. They encode information like this. But what I mean by this idea of quantum data is that you make no assumptions about how you encode your classical information into a quantum state. You're just given quantum states. You're given quantum states by some physical process that you make no assumptions about. And you might then ask, well, like, where does this come up in machine learning? And the answer is I don't actually know, but I think it's relevant for like a lot of physicists actually, because they run and chemists even, they run a lot of experiments in the lab, and what comes out of these experiments are data that they then go and process for various reasons. So you can imagine like some sort of physical experimental setup that contains data that comes to you in the form of quantum states. And so this is what I mean by quantum data. And now what I mean by quantum memory is, well, if you have a way to take these quantum states that come to you from your experiments and efficiently transduce them, so efficiently store them in quantum memory, so in memory, right? So you've got states coming to you and you can house them. And then you can house them and directly process them on a quantum computer. This is an idea of quantum memory. And this is not something so far-fetched. This is something that people are working on. This is the idea of quantum sensors that basically take these states that come to you and then kind of process them thereafter on a quantum computer. And why am I telling you this? Well, I'm telling you this because these kinds of experimental setups, when you have quantum data given to you that you make no assumptions about, and you can use them immediately on a quantum computer, there are interesting learning tasks that people have shown you can do. Like you can perform learning tasks there that you need exponential resources to do otherwise, like classically if you just have like sort of, if you have no access to quantum memory, then this makes this task quite hard. So this might sound a bit convoluted, but all I'm trying to say is there's exponential separations that exist for certain learning tasks. So this idea of quantum memory is actually quite powerful and something that I think a lot of people are working towards experimentally. And theoretically, there are known results for learning tasks that are really interesting. So I can also like provide some links to some papers if anybody wants to read about this. And these learning tasks are of course right up our alley in machine learning, right? Where we're often trying to like learn or approximate something with some goal in mind. So I think this is like a really interesting area. And how this quantum memory will look, again, like I don't know. I think this is something for experimentalists to comment about and think about. But from a mathematical point of view, this is actually also super beautiful, why we get extra power with having quantum states in memory and being able to process them. So remember I spoke initially about when we measure a quantum system, we collapse our information to something classical, right? So this is like, we kind of destroy our quantum information. But when we have multiple kind of states in memory, we can design a measurement in a very clever way that it doesn't entirely destroy our quantum information. So we can measure our system without destroying all our information. And if we do that, we can then reuse it, right? We can reuse our information. So this is like the trick to having like access to quantum memory, is that we can start to do like more interesting things. Theoretically, we can start to like design measurements in the lab such that we don't destroy our quantum information entirely. And so for machine learning, this is really nice because, well, if we can reuse our quantum information, maybe we can kind of track, things in between and like reuse stuff and create efficiencies and learn things more efficiently. Yeah. I hope that makes sense.
Nice. Yeah, that does make sense. And here's a really dumb question.
All right.
But does quantum memory somehow resolve the issues that you were mentioning right from the beginning of the episode around when we try to measure qubits, they collapse into like a known state. Does quantum memory somehow get around that and allow us to maybe, like you were mentioning, how we can't copy information, but maybe we can't copy quantum information, but maybe somehow quantum memory allows us to do that to some extent?
Yeah, this is a really great question, and so I should probably say it's there's a trade-off that exists between how much information you can extract from your system and how much you disturb your quantum state, right? So how much information you destroy. So there's a trade-off there.
Right.
And when you have when you have access to quantum memory, so multiple quantum states in memory, you can kind of design things in a way that you can extract more information whilst not destroying too much, right? So you can kind of extract more than you can with just one state at a time. So this is like the intuition, and so it kind of resolves a little bit this idea of being able to reuse information, because now you can design measurements in a bit of a clever way. So it's strictly more powerful than just having one state at a time. But it doesn't completely resolve it, because indeed you are still, you still need to measure, and you still need to extract, and you still need to destroy or disturb your state. So the idea, like from a research point of view, is how do you do this in a very elegant manner that you extract enough information out with the resources you have, right? So a lot of people are trying to say, well, if I just have a reasonable amount of quantum memory, can I achieve some learning task in an efficient manner? Something that doesn't require exponential time, something like this. And it turns out there are some learning tasks for which this is plausible. You can solve things in an efficient amount of time if you have a reasonable amount of quantum memory. And if you don't have this quantum memory, then you run into costs like exponential time. So this, I think, is quite cool. Yeah.
That is super cool. Okay, so this reminds me of an analogy that a teacher, it might have been like a high school teacher, said to me so long ago, which is, yeah, it must have been like in a high school physics class or something, that the reason why, like an analogy to kind of think of for why it's so difficult to measure aspects of systems that are so small, is that it would be like if you had a little puddle on a sidewalk, and you used a thermometer the size of a skyscraper to measure the temperature of that puddle, you're going to end up changing the temperature of the puddle with your gigantic thermometer. And so the closer you try to get to the puddle, the more you mess up like how accurately you're getting the temperature of that puddle.
Yeah, indeed. I think yes, and I think there's also like a whole. If people are interested in quantum mechanics, there's this whole field of open quantum systems, which I think fits very nicely in what you're describing, right? It's like in reality, we don't have these perfect closed systems that we can just implement in a lab. There's interactions within the environment, like this puddle thermometer analogy is perfect for that. Like we actually need something more realistic, and this is this field of open quantum systems that tries to understand if you have interactions with an environment, how do you model these more accurately? And there, I think things very quickly become quite complicated. But indeed, I think it is relevant. Yeah.
Right. Is this I'm really scratching at some vague old memories here, but this is like I think the thing that I was just describing with the thermometer and the puddle was related to the Heisenberg uncertainty principle. Um anyway, I
um,
so I don't know
maybe
how relevant that is here. Okay,
maybe,
yeah,
yeah, maybe. I don't particularly see. I guess like, yeah, that the uncertainty principle is also, I think, quite straightforward to understand, right? Like it's like if you're trying to zero in on one component of your system, then you kind of lose information about another, and vice versa, right? So
yeah,
so I think this is I think it, yeah, you can kind of also relate this a little bit to this information disturbance trade-off that I mentioned, right? It's like if you want to kind of get a lot of information out, you're going to disturb your state quite a bit, and vice versa. If you don't want to disturb your state, you're not going to get that much information out. So yeah, I guess
right.
in some sense it's similar. Yeah.
So all right, what's next for you with your research? So yeah, like you know, I guess actually, what's kind of like a main takeaway from the quantum neural network stuff or other papers, that you've had that you think would be relevant to the audience? And then like, what's exciting for you now? Like, what are you working on now? And so what do you think,
Yeah, sure.
what breakthrough might be next?
Yeah, sure. So personally, I mean, I joined the University of Amsterdam, and their quantum computing group there is called QSoft. I joined them because they're one of the strongest teams. This is a no-brainer. They're one of the strongest teams from the point of um, quantum theory, and in particular, like complexity theory. So I mentioned this a bit earlier. It's like the study of the hardness of problems and where can quantum computers be useful in this idea. So quantum complexity theory is something I have now become really interested in, and I'm in no way an expert, but I think if we want to be able to say something rigorous even about the types of machine learning problems that we're going to hope to solve or make more efficient with quantum computers, we have to understand things from a theoretical computer science point of view, and this is where this complexity theory comes in. So I joined this group because of they're quite strong in this area, and I would really like to grow my expertise there and then see what we can do potentially for machine learning and so on. But I think there are a lot of open questions and things that researchers can look at right now. So, for example, I mentioned this problem of trying to train these parameterized, quantum neural networks at scale. We need to find a way to be able to do gradient descent in an efficient manner, like we can with neural networks. So there was this recent work that we did on quantum backpropagation, which addresses this question. And in there's a ton of open questions, like maybe we can find special types of quantum models that train well, that train efficiently, and are useful for quantum machine learning. So we have a couple of ideas in there that if people are interested in, they can kind of just look at the conclusion section and see like, okay, these are some areas that we think might be interesting. So trying to train these models. I do still think that this kernel support vector machine area is something that is interesting, and something there that can be found that's quite useful to find an interesting feature map that is relevant for a particular type of data set. So I always encourage people to start there, especially if they're coming from classical machine learning. I think this is the most natural way to think as well in terms of quantum machine learning. So I think this is rather cool. And I'll make the pitch again for quantum memory. So having access to multiple copies of states at a time and figuring out what it is we can learn with this added ability from a theoretical point of view, I think is understudied, and I think there's a lot to say there. I think so in particular, like for example, Robert Huang, Jared McLean, and others from Caltech and Google, they have had a series of papers that show in a machine learning setting there are learning tasks for which we can solve efficiently with this added ability of quantum memory that we can't do if we don't have it. So I think this is a really interesting direction, and I think that I think it's probably what I would like to look into a lot in the next year or so. Yeah.
Very nice. Sounds super exciting. And then I would have mentioned this in the intro to your episode, so I don't think I explained this to you before we started recording, but I script an intro and an outro after we record our conversation. And in that intro, I talk about your background a bit. And so prior to getting into quantum physics, you worked in finance. So your undergraduate degree is actually in business and actuarial science. And you got your CFA, which is by all accounts quite a challenging thing to do. And then you worked in the investment industry. And so what happened that you were like, you know what? Because we haven't, we've been talking this whole time and you haven't been like, oh, I need to I'm going to use quantum support vector machines to figure out how to do accounting better, or so like what happened? Were you aware of quantum computing, quantum machine learning kind of in the background, or where did it jump up from and that you were like, this is what I need to spend my life doing?
Yeah, this is always quite funny to talk about, and I think a lot of people don't understand the decisions until I explain them, because I think growing up, I don't think I really even fully understood what physics was, let alone quantum physics. I think in high school, it was my worst subject, actually. Like, I didn't understand anything about it. It was always super intimidating for me. And but I liked math, so I thought, okay, like, to get a good job, my parents also encouraged me to go a little bit into finance. And so I did actuarial science as a degree, and I did the next step was to get a job. And don't get me wrong, I enjoyed it a lot. I liked working in the investment industry, but I just kept wanting more, like and particularly like more of quantitative sort of fulfillment, you know. So I always liked equations and things like this, and so I started learning a little bit. This is how I found machine learning, like literally just on YouTube with like podcasts, like things like this. I started listening to these things and getting interested. And then somehow I eventually went down the rabbit hole of, I think I YouTubed a video about the Schrodinger equation. And this was not on purpose. This was actually, I was like reading up about the Black-Scholes equation, which, you know, is used to model financial instruments. And the lecturer was a physicist, and he related a little bit to the evolution of a particle through space and time. And then used the Schrodinger equation, and I could like follow the math, and then this just was like, whoa, this is so cool. And so I went down this rabbit hole of, okay, what's the Schrodinger equation, what's physics, and then I found quantum physics, and it was all just very lucky, like right time, right place. I wrote to like a ton of professors in South Africa where I live and said, these are the skills I have, you know, can I please like come study physics with you? And one of them wrote back, you know, Professor like Petroccioni from he's now in Stellenbosch, but yeah, he accepted me as a student, and I went back to live with my parents, and I then just got consumed by this idea of quantum physics. And to be honest, back then there was no real obvious direction. I don't think there were a lot of jobs in quantum physics, so my family was super concerned, like, how am I going to make money? How am I going to feed myself? But I think in the end it worked out. I was lucky with timing, and yeah, I think it's okay so far. So this is how I went to this direction.
Amazing. That's such a cool story. I was smiling ear to ear the whole time. It's like, yeah, so great to be able to find a passion like that. And I get the itching for kind of more. My sister, who's actually at the time of recording, she's been staying with me here in New York for a couple of days, but she lives in Toronto, and she's worked in finance for many years. She did an undergrad in financial math, and has been working as a trader for many years, and now is in the ESG space. But something that she had this similar itch to always be like doing the most complex derivatives trading possible, because like I guess people like you and her have such a desire to be like constantly pushing the envelope of your mind and digging into something deeper and building upon the foundations that you have. And I think in finance, you often completely, in terms of practical applications of finance, you start to run into like limits of how abstract or complex the math can be and still be useful and make money.
Exactly. I think
So yeah.
the last part is important about what you said, was like the things that I wanted to do. I don't think anyone in finance cares about that. And that was the problem, I think, was like I was thinking very abstractly, and companies of course have purpose, and yeah, I just wasn't aligned to this anymore.
Yeah. Theoretical finance. I don't know. You don't hear about
That
that too
sounds
often,
nice.
I guess.
No, that sounds, yeah, that
Yeah.
sounds nice. But then you're probably limited to universities, I imagine. Yeah.
Let's imagine everyone has all the resources they need to clothe themselves and be secure and have food. It's a nice theoretical finance idea. Um, so yeah, very cool. Let's jump now to audience questions, because we had a lot of interest in you coming on the show. So for our listeners who aren't aware, for some guests that I have coming up, and I don't do it for every guest, it's I don't have an exact process for this, but I basically think ahead to who am I interviewing next week, and is this somebody that if I'm like, this is the topic that I'm thinking of covering, or this is their background, is it likely to elicit a lot of questions, a lot of interest? And in your case, it very much did. So we got several hundred reactions from people on LinkedIn, tens of thousands of impressions, dozens of comments. And so, yeah, and some amazing questions came up from the audience. Nice. So our first question here is from Annika Nell, and she is actually from Cape Town. So from your part of the globe, Cape Town, and you mentioned Stellenbosch University there recently as being the place where there was a professor that first let you move back in with your parents and do some physics. And so Annika actually she studied physics and math at Stellenbosch and computer science as well. Now works as a back end developer in Cape Town. And Annika is wondering for people looking to do their post grad in uh, it says this field, so I'm assuming quantum machine learning. Yeah, how does somebody get the right background? I guess it's they watch one YouTube video on the Schrodinger wave equation, and then they're good to go.
Oh no, I think yeah, well, that's the spark, and then the rest is a lot of sleepless nights, hard work, and eating and breathing physics, quantum physics, till things start to click, right? No, so I think for people in South Africa, I can immediately say, okay, well, Francesco's group at the University of Stellenbosch, if you're interested in quantum machine learning, this is the way to go. But for other people in other countries and other places, this is it's not so easy to always figure out who to contact and what to do, right? So if you're interested in quantum machine learning, I'd say start by first figuring out what it is you're interested in the field, like within the field, right? Because it's quite broad. So there's a beautiful textbook that's now I'm again gonna give a shout out to my professors. So there's a book called Machine Learning with Quantum Computers that was written by Maria Schultz and Francesco Petruccioni, who were my PhD supervisors. But this textbook is absolutely beautiful. It covers almost everything there is to cover in quantum machine learning, all the aspects, all the different types of things, all the moving parts. And it's also super digestible for someone who is not a physicist. So someone like me, for example, I wasn't a physicist by background, but I could pick up this book and I could kind of make sense of it after a couple of reads. So I'd recommend starting with something like this. And within this textbook, there are references for each section and each thing. So if there's something in there that like piques your interest, you can kind of look at the reference and see the paper and see the authors of the papers. And there you can start to gauge, you'll see immediately some commonalities in like who's writing the certain types of on the research on the topics that you like, and just reach out to them directly. I mean, academics in particular are super approachable. It might seem strange to just send somebody a random email if you're coming from the investment industry or like any kind of industry, but in academia this is totally normal, right? Like just reach out and say, hi, I've read your work and I have a question about it and I want to study it, or I want to do my postgrad. And 9 times out of 10, if you structure the email appropriately and positively, and you show your enthusiasm, you convey that spark of interest, someone will help you. So I think this is a way to go, and this is kind of like what I did, right? I wrote emails to everybody, even though nobody knew who I was. I was totally random. I had no skills, but I was persistent. So these are the two things: like be polite, be persistent, and find research groups like
Positive.
this. Yeah, yeah, and positive.
Polite, persistent, and positive.
Three
The three
Ps
Ps of academic reach outs. You heard them here first.
Yeah, we should patent it, but it sounds so cheesy and so stupid. But I mean, this is like really the advice I can give, and yes, university groups in particular are rather responsive, and they're always usually looking for people to do postgraduate studies in. So I think this is not too difficult these days.
Very cool. Great answer there. And that ties into some other people's questions. So Sinchan Bhattacharya, who's a principal data scientist, also asked, what's the pathway to becoming an expert in quantum machine learning? And so I think you answered that question. We had several people just ask for applications of quantum machine learning. So Saad Jamshed asked for that, as well as John Hawkins. So yeah, I think we've covered that already clearly in this episode. Saurav Bakshi has a question that is, I guess it kind of extends from that. And maybe we didn't answer this sufficiently when we were talking about quantum machine learning use cases before. So Saurav asks, which use cases in quantum ML can be used by business right now? And I think we've answered that in this episode, and that it's probably nothing right now. But what about in the future? Like, do you see mainstream applications of quantum machine learning emerging in the coming years? Like, where might that be?
Yeah, this is a really, really great question. And I must kind of declare immediately that I've been feeling a little bit less optimistic about quantum machine learning than in I kind of go through waves, right? I think most researchers experience this. They're usually some ups and then some downs, and I'm kind of on the downside right now because I think I've been trying to make, not just me, like a ton of people have been trying to make a lot of things work, and we just can't seem to do it, right? But that doesn't mean that that the whole field is doom and gloom. And in terms of business applications, I think people in business really don't really care if from a complexity theory point of view we can't solve MP hard problems or whatever. They don't care, right? I mean, if a heuristic approach, something just like a try and see quantum algorithm works for some reason, even if we don't understand it theoretically, this is like gold, right? So I do think that there are use cases for quantum computing in fields like optimization, for example, where we can provide speed ups to problems that are practical and useful. We just have to find them. So we haven't found them yet. And from a research perspective, this is super attractive, right? Because there could be a lot of low hanging fruit for people. So I do think the field of optimization is something that's naturally suited for quantum computers to perhaps add speed ups to, or perhaps add new algorithms to. In terms of machine learning, where we can see some advantages, I do think from a theoretical point of view, going down this line of having quantum memory and stuff like that, exploring this a little bit more, is something to look at. But in actual fields, I don't know. People often ask me because of my finance background. Can we do things like I don't know, speed up the models that we have to price derivatives or something like this? Like personally, I don't think so. I don't think that quantum computers are going to add anything beneficial there. Um, I do think that they offer some basic speed ups under some very, very restrictive assumptions, but these don't hold in practice. So to be honest, I don't think finance is a killer application yet. I hope to be proven wrong. I think maybe in healthcare we'll see some interesting things because there's a lot of chemistry, and material science chemistry is something that's very difficult. Interactions of particles and things like this are difficult to simulate naturally on a classical computer. So maybe there's stuff we can do and say. And there's a whole field of quantum chemistry as well, which links a little bit to machine learning. That's super interesting. So I think probably from a business point of view, that's where we'll see a lot of killer applications in the near term. And yeah, and then I mentioned optimization, which of course ties into logistics. So maybe this is also something we can see some practical speed ups in.
Very cool. So yeah, so you see the most fertile ground going forward in kind of healthcare applications because of it seems like there's a lot of opportunity for quantum computing in chemistry and materials. And then in addition in logistics. And that's great. That's so crystal clear. And it's interesting. We have a question from one listener. So Doug McLean, he's a lead data scientist at Tesco Bank, and he has probably the single longest, but also most wonderful question that's ever been asked when I do this, when I ask for audience questions. And I think there's no point in me kind of reading it all, but we'll be sure to include a link to this post in the show notes if people want to dig into it. So Doug had an amazing question, but it's all related to stochastic processes in derivative pricing. And I don't think he knew. I actually didn't mention in the post about your finance background. So he either did some research on you separately, or it's a coincidence that this amazing question about derivatives. But it sounds like, you've already kind of given the answer on derivatives pricing, and there probably being relatively limited application areas there, at least so it appears right now. So this brings us to our last question asker, Jonathan Bound. So he's an ML ops engineer, and he had 3 questions for you, some of which you've already covered. So one was on, specific advantages of quantum machine learning relative to classical machine learning. And his second question is great. I think this is a perfect next question for the podcast episode in general, which is, if a listener wants to build a model using quantum algorithms or methodologies, what tools are practitioners using? So Jonathan is familiar with Qiskit, Qiskit, and he's seen a few projects on Kaggle using it for model pipelines. But are there more machine learning specific tools out there for people interested in quantum computing?
Yeah, cool. This is such a nice question, and in fact, all of them have been. So thanks everybody for the questions. And um, indeed, there are quantum machine learning pipelines. The ones that immediately come to mind and are my favorites is Penny Lane. So Penny Lane is a package released by the company that I mentioned earlier in Toronto, Xanadu, specifically structured for quantum machine learning. And I think it is super nice, really well documented, really easy to use, a lot of tutorials. And they also do this wonderful thing where they kind of take interesting new research that's published in the field of quantum machine learning and then add code to it. They add like a whole Penny Lane walkthrough. So pennylane.ai, I think, is the website to go to, and it's really, really cool. It's really great for quantum machine learning. They even have a whole explainer walking you through what it means to do quantum machine learning, to encode data, how you can consider encoding it, how you can get labels out, how you can do certain machine learning pipelines and so on with a quantum computer. And you can also very naturally use their package to plug into actual quantum computers as well. So you can plug into actual devices. So this is a super nice one. Google also, so I should probably say Qiskit is IBM's open source framework, right? So, but Google also have one, and theirs is called TensorFlow Quantum. So if you are familiar with TensorFlow, then you'll pick up TensorFlow Quantum like that. And they also have some really nice documentation, some explainers, and I think that their machine learning stuff is really nice, and they also have another quantum computing sort of framework called Cirq, CIRQ. So Cirq is also great, and these two things, TensorFlow Quantum and Cirq, go nicely hand in hand. So yeah, so I think these are some of them. There are some ad hoc other things, but I think if I were to start personally, I would start with Penny Lane, and then if Penny Lane is not giving me what I want, I would then go and look at Qiskit and TensorFlow Quantum and so on.
Awesome. Yeah, I remember when I first started looking to do a quantum machine learning episode a couple of years ago, I remember coming across Penny Lane as well as being I was really impressed by the thoroughness of the resources and the hands-on code demos. It seemed like a really cool resource. Awesome. And yeah, then Jonathan's very last question there. It sounds like something we've already addressed now. So he says, do you see quantum machine learning becoming as popular as something like open source large language models are right now? And I think, unfortunately, we've already kind of heard that, at least on the ebbs and flows of your personal excitement about it, it seems like right now, maybe that's something that's hard to visualize. But I guess maybe looking longer term and just with, in 2012, or maybe even more appropriately in 2010, 2 years before Jeff Hinton and his team had released AlexNet and demonstrated how powerful it was at deep learning, probably people working on neural network research they wouldn't have imagined that in 2023, we'd be where we are today with crazy capabilities like we see in GPT-4, powered by these large language models that run on deep learning, and everybody in the world being excited about these applications and the fastest growing consumer applications. So there's hope yet.
Absolutely. Yeah. I don't want to crush anybody's dreams. If people are super excited about quantum machine learning, you have the right to be. There's so much we don't know, and that's part of the allure of the subject, right? But maybe my negativity, or my pessimism, I should say, kind of just comes from the fact that there's a lot of hype with nothing to back it up. And this is what I don't like. And so people must just be a little bit cognizant of the fact that there aren't these blanket results that just say quantum computers are going to provide us with exponential advantages and so on, because it's far, far more subtle than that. And indeed, we can dream big, and we can hope for, and we can try, and we can explore, and that's all wonderful, and that shouldn't be taken away from this conversation today. Yeah.
Yes. And for people who want to dream and explore with you, they can do that, I understand, upcoming at UCLA. So you will be one of the instructors for an in person quantum machine learning course. Do you want to tell us more about that?
Yeah, sure. So the Institute for Pure Mathematics, I think it's called, the IPAM, Pure and Applied Mathematics, I think is the acronym, at UCLA is hosting it's actually a month-long series of talks on the theoretical aspects of quantum computing and quantum learning. But there's a particular week in there, the week of October 17th, where it will just be focused on quantum learning theory. So specifically like mathematical aspects of quantum machine learning and these kinds of things will come up as topics. So if people are interested, you can register for this and attend some of the talks. I'll be teaching, a couple of other people will be teaching as well. We can make the links available. And yeah, I think it should be a great place to discuss research, to see what's going on, what some of the latest results from people in industry and people in academia are doing.
Fantastic. Well, after years of personal hype for me about getting a quantum machine learning episode, you have exceeded my expectations, and this has been so awesome. I've learned so much on something that I knew so little about, and so I hope, yeah, I'm sure, actually, I don't need to say I hope, I'm sure our audience members learned a ton as well. Amira, thank you so much for taking the time today. Before I let you go, we always ask our guests for a book recommendation. What have you got for us?
Okay, sure. I should start by saying I don't. This is very embarrassing, but I don't like read a lot of books outside of textbooks. So my recommendation is going to be a textbook, just like a
No,
teacher.
that's great.
But like I started going down this rabbit hole of complexity theory. So I want to maybe give a shout out to one of the best books that I've come across so far, and it's called Computational Complexity: A Modern Approach, and it's by Barak and Aurora, who are really, really badass like complexity researchers. And in there, they cover kind of everything you need to know from a theoretical computer science point of view for classical and quantum. So it's really quite beautiful, and you don't really need much expertise. They kind of walk you through from the basics to the most advanced. So if you're interested in some of the stuff that I spoke about today, I think this textbook is like, oh, and I think there is a free copy available online if you just Google it, which also makes things a lot nicer. So yeah.
Brilliant. And then, yes, very, very last thing, Amira, is with all of the brilliant insights that you've been able to provide today, I'm sure a lot of people will want to know how to follow you after this episode and get your thoughts. Where should they do that?
Yeah, sure. So I guess I'm probably most active on Twitter and LinkedIn. But if people are, wanting to discuss like serious aspects from a research point of view, I'm also available. I think the best way to contact me is via email. But yeah, I think probably Twitter and LinkedIn. And I tend to share, I think, a lot of events and papers and new research and stuff like this that are within the field of quantum machine learning on LinkedIn. So I think that's probably the best bet if you want that. If you want to chat, then via email. Yeah,
Perfect. Yeah, we'll be sure to include links to
great.
all of those options in the show notes. All right, Amira, thank you so much. And yeah, hopefully we can check in again in a few years and hear that there's been amazing strides made in quantum machine learning. And
Yeah.
yeah, and it's all excitement and no hype.
Yeah, I hope so. Thanks so much for having me. It's been great to chat. And yeah, we'll see how it goes.
How exceptionally gifted Amira was at identifying the most interesting paths to flow through our conversation. I was left feeling like this episode had a perfect arc to it from beginning to end. In today's episode, Amira filled us in on how qubits have probability amplitudes that are much more nuanced than classical computing's bits. This allows for more efficient computing for specific problems such as prime factorization problems, but quantum computers may need to be scaled up many orders of magnitude from where they are today in order to provide practical value for machine learning in the years to come. She filled us in on how quantum machine learning involves 3 distinct steps. The first is converting data into a quantum state. The second is evolving, that is performing operations. And the third one is converting the result into something interpretable, such as a vector of numbers. She told us how quantum support vector machines have been demonstrated to be more efficient than standard SVM, but the data used for these demos so far are too contrived to be likely to be observed in practice. And then she left us with the software libraries that she recommends checking out if you're just getting started with quantum ML. Specifically, she recommended Penny Lane, IBM's Qiskit, or Qiskit, I don't know how to pronounce that, Qiskit, Google's TF Quantum, and Google's CIRQ, CIRQ. As always, you can get the links to all of those libraries, other materials mentioned on the show, all the show notes, including the transcript for this episode, the video recording, and the URLs for Amira's social media profiles, as well as my own, at superdataScience.com/721. If you would like to interact with me beyond just the podcast or social media, coming up on November 8th, I'll be hosting a virtual half-day conference on building commercially successful LLM applications. It'll be interactive, practical, and it'll feature some of the most influential people in the large natural language model space as speakers. It'll be live in the O'Reilly platform, which many employers and universities provide you access to already. But if you don't already have access, you can get a free 30-day trial of the O'Reilly platform using our special code SDSPOD23. We've got a link to that code ready for you in the show notes. All right, thanks to my colleagues at Nebula for supporting me while I create content like this Super Data Science episode for you. And thanks, of course, to Ivana, Mario, Natalie, Serge, Sylvia, Zara, and Kirill on the amazing Super Data Science team, the Super Data Science team, for producing another mind-blowing episode for us today. You can support this show by checking out our sponsors' links, by sharing, by reviewing, by subscribing, but most of all, I hope you just keep on tuning in. I'm so grateful to have you listening, and I hope I can continue to make episodes you love for years and years to come. Until next time, my friend, keep on rocking it out there, and I'm looking forward to being over this cold and enjoying another round of the Super Data Science podcast with you very soon.